call this file Introduction to FFT and .m. So I'm just going to copy this, and I'm going to hit save, and then I'm going to save this in a file or folder that I like. So save. I'm going to start defining a cell. We're going to say example, and we're going to calculate the Fourier transform of this e to the negative 2 times t over the interval 0 to infinity, basically. So we multiply it by a unit step function. Also, I'm going to say here, we know that the solution to the solution is g of f is, because we did this in class last time, but it's going to be like this: 2 plus j2 times pi times f, and all that's raised to the power -1. And so we want to know, how does this compare to the FFT result? Okay, so first off, I'm going to define let's define a t0. So let's let t0 be 4, right? So what is this? This is, I'm going to add comments. I'm going to say this is seconds, and this is the signal window, right? So also let's have a sampling period, and we're going to let that be 1 sample every 64. Let that be 64 samples every 1 second. And so that's a second thing, second value, and this is the sampling period. That enables us to calculate the number of points. So n0 is t0, so that's the whole interval divided by the sampling period. And then t, we're going to let t be a time vector. Say I'm going to go from 0 to n0 minus 1. So that's going to give me a set of integers, right? And I'm going to multiply it by ts. And there's one other thing I'm going to do to this. I'm going to put it all in parentheses, and then I'm going to transpose it. So that's this little thing. The reason I transpose it is FFT likes column vectors, not row vectors. So this alone right here is going to give me a row vector. So I transpose it to get a column vector, and this again is it's our time vector. Oh, and let's put a semicolon after this because we don't want to see this, 264 time points. We're going to define gamma, right? So gamma is this ts times g, where we said that g is the exponential of -2 times t. So remember that FFT does not work on g itself, but rather gamma, which is this thing that I just gave you. Another thing I'm going to do is set the first value of gamma, because you know that g of 0 would be 1. However, with this function, e to the 2 or e to the -2 times u, right? There's a jump discontinuity. Where's the jump discontinuity? At 0, there's a jump discontinuity because before 0, the function's 0, but just after 0, it's approaching 1, right? So there's a jump discontinuity, and so what we have to do is we have to set this, where there's a jump discontinuity, we want to set our function to be the average of, and I'll just say 0.5 because that's the average of the points on either side, right? So 0 and 1. So this is, and what we can specify here the units. So right here, we're going to assume that this is volts. This is some electrical signal. And actually, it's not volts, it's volts times seconds because we're multiplying by TS, right? So also down here, we'll put that in. It's volts times volts times seconds. And this is the average of points on, we'll say points surrounding jump discontinuity. Okay. Before we run it, let's set up our publish settings. We'll go publish. So you got to hit the publish tab up here at the top, and then there's this publish thing, green arrow document, and then I'm going to hit edit publish options. It brings up a publish window, publisher options, and I want to change the file output from HTML to PDF. And I'm going to leave everything else the same. So I'm going to close it, and just to make sure things run right, I'm going to go back to the editor, and I'm going to hit run. And I'm not in the folder that my file's in, so I'm going to hit change folder. That's okay. It runs it. I don't see any errors. That's good. Okay, so now let's actually take the Fourier transform. So G equals FFT of gamma, big G, is FFT of gamma. And this did not, I didn't specify the number of points, so it's going to give me NO, where I believe NO is 256. Let's look at the workspace just to verify that. Yep, NO is 256. So I'm going to go back to the command window. Okay, and now we want to plot things. So let's get the magnitude, absolute value of G, and then the angle, so GP for phase, angle of G. But I don't know about you, I much rather like to think in degrees rather than radians, so we'll do that. And now we can plot, and let's say we'll say new figure equals figure, and then let's say plot, and we're going to plot GM so with respect to f. So you type f comma GM. Now this brings up something. I didn't define the f vector yet. So how do we define an f vector? We know that since we didn't specify the number of frequency points that we want, it's going to be the same as the length of gamma, right? So, but we know the length of gamma is n0. So let's say f goes from, it's going to go from 0 to n0 minus 1. Same trick as before, but the discretization is f0 in frequency, right? So we're gonna actually just divide by t0, because divide by t0 same as multiplying by f0. Okay, so now we can plot. There it is. Here's my figure. And you may recall that there are some formatting things that I really like. Well, first off, I like to set, I set the line width to 2, and I like to turn the grid on, and I like to set the current axes, so GCA, font name to times, font size to 24. Now this is the beauty of writing code, is that reusable code can be so powerful. So I'm going to copy this formatting stuff that I like, and I guess as an aside, let's run it just to make sure it works. There's my document right there, or there's my figure. Let's just bring up a new script. So go up to the left here, hit this new down arrow, and I'm going to call it my standard plot format.m, right? And then I'm going to paste in those commands that I like, and then I'm going to copy this name, my standard plot format, copy, and hit save, and then I paste it in there. So then I can invoke this whenever I make a new plot. So instead of here, I'm just going to type my standard format, my standard plot format, and then for now, I guess we can comment this new figure out because it's going to keep bringing up figures, and I don't want to do that at this moment. And then I can run that, and there's my result. So that's not quite helpful. So let's add a little bit to it. We'll say subplot 2, 1, 1, and then we'll bring right below it, we'll bring up another subplot, but it's going to be 2, 1, 2. And here we're going to plot F, and we're going to plot GP. And I'm going to copy the same thing. I like the line width and the standard formatting. So I hit run, and then it looks like that. So we know the form of the real answer, right? So let's compare our result to the real answer. And so since we have this F vector, we can calculate the analytic solution. So we'll call it big G and then AS for analytic solution. And we're going to type in 2 plus, and then how do we do a J in MATLAB? Well, we type 1I times 2 times pi times f, and then we have to invert that. So we're going to do a dot to the power. So this is an element-wise power to the -1, and that should be our answer. So we're also going to take the magnitude of that is abs of that, and the phase of that is angle of that. But just so we can compare apples to apples, we type 180 over pi, so we're comparing degrees to degrees. And then in my plot command, I'm going to put GM and then semicolon and GASM and GP and G analytic solution P, like so. And then I can just hit run, and let's see how that works. Oh, it didn't like it. Why not? Oh, okay. The dimensions are not consistent. So I believe GM is it might be a column vector, whereas the other one is a row vector. So let's try transposing GM and GP. Let's see if that helps us. Okay, it did. But let's see, there's an issue. I'm not sure what it is. Let me see. Issue. Oh, here's the issue. Okay, this first thing, I just gave it 1/2, but what do I need to do for gamma 1? What's missing? I need to multiply it by TS, right? Because here, if it was just 0.5, it would be a voltage value, and now it's voltage times seconds like the other one. So let's hit run, and oh, let's just put in some stuff here. At the bottom, let's put X label, and let's put in F for frequency, and its units are hertz. And we'll also put in for the second subplot, we're going to put in Y label is angle of G, and the units are going to be in dollar signs. We're going to put caret, and then braces, and then backslash and circ. So that's going to give me the symbol that I want. And then for the first subplot, so before I type subplot 212, I'm going to put in a y label, and I'm going to put in, this is the magnitude, so it's going to be vertical line, or pipe as they call it, pipe G pipe. And the units here are volts. Okay, so let's run this. And it didn't like that. You can see the picture, they're not pretty labels, so what I left out was interpreter and LaTeX. So I'm going to copy that, and I'm going to put it in the other places too where I forgot. If I run it again, now my labels look very fine. So why is the analytic result in red different than the blue one? I mean, they're the same for some part of the problem, but different elsewhere. Why is that? The duration of the computer version, right, is finite. So when you take a finite duration, you end up with a periodic result, right? And so this this blue one, the computer version, is periodic, and so up to about half of the, up to about, because this goes to what, 64 hertz, up to about 32 hertz, they match nicely, and then they diverge. So there's another thing that we can do, is we can say, hey, let's forget about the other half, and we can just plot half of it. Or there's another thing where I'm going to start a new cell here, and I'll show you that. It's I'm going to say we're going to call it the zero-centric FFT result. Okay, so here, what I do is I'm going to use a function called FFT shift, and so I feed it the results of a Fourier transform, so FFT of capital G, and we're going to call it GZ for, we'll call it GZC for zero-centric, okay? And then our frequency vector then, we're going to call it FZC for zero-centric. It's going to go from negative n0 over 2 up to n0 over 2, but we're going to subtract 1. This is going to give me n0 points plus 1, because there's 1 point at 0. We subtract 1, so we actually get n0 points. Okay, and we have to multiply that by the frequency discretization, which is 1 over t0, or just f0. And now we can say GZC magnitude is abs of GZC, and GZC phase is the angle of GZC times 180 over pi. And then now I'm going to copy from above and just paste it. And we have to change some things here. So we're gonna plot. I'm just gonna get rid of this whole thing, and I'm just gonna plot GZCM, the magnitude, and down here I'm gonna get rid of all of that, and we're just gonna plot the phase. And then if I hit run, now, oh, and I can't use F. I have to use FZC. That's what, FZC. And so if I run this, now I have my nice zero-centric magnitude and phase plot. And then if I go back to the Publish tab and I hit Publish, then it should give me a document in PDF that just came up on the other screen. So let's look at it. So here's my document in PDF, which, again, this is what you're doing for your project. So there's the code for section 1, and then the output for section 1. And then there's the zero-centric result, like that. So you can see that our discrete time Fourier transform actually matches very nicely with the analytic solution over over some interval. So that's nice.